Me, okay. Well, thanks very much for the introduction, and thanks to Vincent for the invitation to come and speak today. I realize, first of all, that I'm the last speaker of the day, so I'll try and be relatively brief so that we can all take a much-needed break and have a cup of coffee. I'm also, there were three very interesting talks today, so I've got three very difficult acts to follow. One of the common themes that I noticed across the three talks is that there was a demonstration of a new tool or a new methodology that allows us to ask new kinds of research questions. So I'm going to try and spin my talk in that direction and talk about a particular methodology, which is where we allow the body plan of our physical robot or our simulated robot to change over an optimization process while we're trying to generate some useful behavior for it. So as David mentioned, it's very difficult for a physical robot to change its morphology as we go along. It's difficult but not impossible. It's much easier in simulation. And so what I'd like to try and do today is touch very briefly on a few robotics projects that I've been involved in where the morphology is somehow changing over the optimization process. As I mentioned, I'm going to touch on these briefly. I'm not going to go into the mechanistic or algorithmic details of how those behaviors were evolved or otherwise optimized. I'd like to try and stay away from the how questions and focus more on the why questions. Why, as embodied cognition practitioners, do we spend so much time thinking carefully or trying to think very carefully about what the appropriate body plan is for our physical device or our simulated creature or what have you? So the reason why I wanted to focus on why questions rather than how questions, how do we go about doing this, is based on my own personal observation. As Rolf mentioned, I obtained my PhD in his lab here at the University of Zurich and then followed the relatively rare academic trajectory of having my graduate degrees awarded here in Europe and then taking a faculty position in the United States. So my observation as a junior faculty member now in the United States, as many of you are probably aware, robotics in the United States is viewed as a very pure engineering discipline. So Heinrich gave the example of the DARPA challenges. It's a purely engineering approach where the idea is to realize a better machine, a faster machine, a more adaptive machine, where there's been some very spectacular results, but you see less of the interdisciplinary thinking that we're all involved with here, that you're all involved with here, that you tend to see in European research and Asian research that hasn't quite reached the United States yet, at least in my opinion. It's starting to, and so coming from Europe, if I give talks about evolutionary robotics, I will typically get the constructive criticism at the end of the talk about why bother? Why go through this extra effort of trying to build in models of biological evolution or to try and build in some developmental mechanisms? If you're interested in legged locomotion, for example, why don't you just start with your legged robot, optimize a control policy for that robot, and be done with it? Why go through this evolution? Why go through this extra algorithmic complexity? So what I'm going to try and do today is to show you some lines of evidence that hopefully will convince you. Again, this is the first time that I've given this talk, so I'm hoping to take it back to the US and see if I can convince any hardcore roboticists there. So that's my idea. Obviously, also, we have some time for discussion later on this evening. So what I'd like you to do in the back of your minds is think about your own research programs and imagine that you could fundamentally change the body plan of your robot, your device, your simulation, your simulated creatures as you go along. What new kinds of research questions could you ask about your platform that you're working with? And I hope that'll generate some discussion later on. Just as, again, I don't want to say much about the algorithms. All of the projects that I'm going to show you here are basically evolutionary robotics projects. At their heart, they have some form of a genetic algorithm or evolutionary algorithm. A GA is basically a very, very rough model of descent with modification. You have some form in which you represent potential solutions to your problem, which might be parameters describing a neural network. You download each of those neural networks onto a physical or virtual machine. You evaluate them. You figure out the relative quality between these different solutions. You discard those that don't do so well and make modified copies of those that remain gain, and repeat. Okay, that's the basic algorithm underlying all of this work. There's different flavors of this, but I'm not going to get so much into that today. So again, if we combine an evolutionary algorithm with a simulation environment, this is a three-dimensional physics-based simulator. So you're watching an animation, but